Okay, we are back. So this is our one and only tutorial video on chemical names and formulas. So what I'm going to do with this video is I'm going to walk you guys through the logic, the thought processes you need to go through in order to accurately and successfully either write a name for a compound or a formula or both. All right, and it all starts here with our periodic table. Okay, and so at this point, you guys should have in your head the first thing you need to think about when giving names and formulas is identifying what type of compound it is. Is it a molecular compound, in which case the elements are bonded covalently, or is it an ionic compound, in which case it's two ions that are bonded through electromagnetic attraction. Okay? And I did talk about that in the lecture. Hopefully you guys got to that. How can we differentiate those two terms? But we use the periodic table for that. Okay? And so the first thing to direct your attention, remember this staircase we did back in Unit 2. Identifying things to the right of that staircase and to the left. That's our dividing line between our metals and non-metals. And yes, there's a couple on that line that we consider to be metalloids. Okay? But what we do with that is we use that to determine whether we have a metal with a non-metal or two non-metals, for example. Okay, and that's important because the first thing I want you to remember is if there is a metal, right, which is one of these guys, you automatically know it's ionic. That's the dead giveaway. Okay, if one of these metals here is present in your compound, it's ionic. All right, now covalent compounds and molecular compounds are created from just this part of the periodic table. Now, our noble gases don't generally form compounds. Now, they can. It is possible. It's just they don't generally have a need or tendency to do so. All right? So we're talking about compounds that form from this small section of the periodic table. Those are our molecular compounds. And they can do so in a variety of different ways. Just because there's not very many elements doesn't mean there's not a lot of molecular compounds. There is a lot. Okay? But when we restrict ourselves to this part of the periodic table, we are talking about molecular compounds. Okay? When there's a metal involved, we know it's ionic. And the only other thing to remember is polyatomic ions. They're a little more complex because they are actually molecularly bonded and then they form an ion. So polyatomic ions still form ionic compounds. And I want you to remember that. And the name should give it away. Polyatomic ion compound. All right? So here's what we're going to do. We're going to flip the chart up, and before we actually go through and write formulas and names, we are going to identify our compounds as either ionic or molecular. And I'm just going to use an I or an M for those, okay? So here's our list. Let's start on the left here. Okay? Silicon and hydrogen. Okay? Now, hydrogen can be a little problematic. Okay, because sometimes it forms ions, sometimes it forms covalent bonds. It really depends on what it's bonding with. Now, an easy way to tell without understanding electronegativity is to look at where it's written in the formula. Okay, because hydrogen, if it is an ion, is going to be a positive ion. All right, and positive ions are always written first in a formula. So this right here, because it says silicon and then hydrogen, that tells you that that is not a hydrogen ion. So that is going to be a molecular compound. So I'm going to write a little M there. All right. CO2, carbon and oxygen, both non-metals, no polyatomic ions. That is molecular. Calcium, bromide. Hopefully you guys have your own periodic table in front of you, by the way, so you can double check what I'm doing here. Calcium is a metal ion. Automatic. Manganese and oxygen. Again, manganese is a metal, ionic. Iron, metal, ionic. Hydrogen again. Uh-oh. Okay, so again, when we see hydrogen as part of our compound, we need to be like, okay, wait. How do I know if this is ionic or covalent? Because it's hydrogen. Okay? Look at where our hydrogen is written this time. Hydrogen is written first. All right, so I'm just going to say, when I do that, whenever I write hydrogen first, unless it's water, all right, it's going to be ionic. So I'm going to use my ionic rule, and we should also indicate now, because hydrogen is the cation, I'm going to make a little note that that is an acid. All right? Also an important feature there. Okay, so we're starting to add little things that you need to catch by being careful. So I think it's a very good idea to survey the list and go through and make these notations before you even start to go name them, because you're going to get in a hurry and you're going to make little errors, even though I know you know better. You got to try to avoid that. All right, we got N2O5, nitrogen and oxygen are both nonmetals, so that's molecular. PCl4, phosphorus and chlorine, nonmetals, molecular. Aluminum phosphate. All right, aluminum is a metal, that's ionic. Okay, now it's a little easier when you're given the name to write the formula because the name kind of gives away whether it's molecular or ionic, but let's go through that process anyway. Tin oxide, tin is a metal, that's ionic. Calcium chloride, calcium is a metal, ionic. Dinitrogen tetrasulfide, nitrogen, sulfur, two nonmetals. Molecular, ammonium nitrate. Now, ammonium and nitrate, neither of those are metals, okay, but they are both polyatomic ions. I put this one up there on purpose to catch that. Ammonium nitrate, two polyatomic ions, that is an ionic bond. Hydrobromic acid, right? Whenever it's an acid, we know hydrogen is a cation, it's ionic. Phosphoric acid, ionic. Aluminum hydroxide, which is metal, ionic. All right? So, you've done that. Again, that doesn't take very long, but it's going to help you avoid mistakes. If you survey everything in your list first, identify which are molecular, which are ionic, because we need to use different rules when that happens. All right? So, next thing we do then is we use our periodic table. And the rules we've learned in chemistry to identify the names for these and the formulas for those guys. I'm just going to walk you through that. I'll go a little slow at first, and then I'll pick up the pace. What I recommend you guys do at home is you pause me, right, and try to do some of these yourself, okay? And get good at identifying whether it's molecular or ionic, okay, first. Then remember the rules and how they're different from molecular and ionic, and then we go through the process. All right? So our first one is a molecular compound. When it's molecular or covalent, we need to use prefixes. So I have 1 silicon and 4 hydrogens. Now, with our naming rules for molecular compounds, if the first one is a 1, we don't use the mono prefix. We only use mono for the second one. All right, so this one would be silicon. All right, so 1 silicon, 4 hydrogens, and the prefix of 4 is tetra. So this would be tetrahydride. Okay, also molecular. So carbon, there's only 1 carbon, so I don't need the mono prefix because it's written first. Carbon, I've got 2 oxygens, that's going to be dioxide. All right, here is ionic. So when it's an ionic compound, you do not use prefixes. All right, calcium is a group 2 element, so I don't need a Roman numeral, which we'll get to here in just a second. So this is just calcium bromide. All right. Now, here we have manganese and oxygen. Ionic, because manganese is a metal. All right. Now, you guys should notice that manganese, Mn, is a transition metal. So, with the exception of silver, zinc, and cadmium, our transition metals need Roman numerals. Okay? And I guess you could consider gallium and indium too. You don't need Roman numerals for those either. But because manganese is a transition metal, that means its charge is not always the same. So we need to indicate the charge in its name. So because this is Mn2O3, we need to go back and infer the charge. All right? Now the way we can do that is kind of undo our crisscross. All right? So this is 3 oxygens. So that must mean this is a 3+. This is a 2, right? So and we know oxygen's a 2 minus, right? Oxygen's always a -2. So therefore, I need to name this not just manganese oxide. I need to say manganese 3 oxide. Okay? So when we have a transition metal that is not silver, zinc, cadmium, gallium, or indium, we need to include a Roman numeral to show what the charge of that transition metal is. In which case, you're going to have to use that formula to figure out what it is. All right? Iron and oxygen. Okay? Iron is a transition metal, so we need to go back and infer the charge. Now, it says I only have one of each, but oxygen, I know one oxygen is a 2 minus. Right? If it's one of each, that must mean that the iron is not 1 and 1, it's 2 and 2. So this iron must be a 2 plus, right? Therefore, my name is going to be iron 2 oxide. All right? HCl, ionic because the hydrogen is written first. Now, I made a notation here. When hydrogen is my positive ion, so when hydrogen's ionic, that means I'm making an acid. All right? Now, the next part here that tells me how to name this in terms of my acid rules is to look at whether this is a polyatomic ion and an 8 or just a monoatomic ion. So because chlorine is monoatomic, that means I need the hydro prefix for my acid. This is going to be hydrochloric acid. All right, if you can't remember those acid naming rules, look back at your notes. All right, next one down, N2O5, it's a molecular compound. Molecular means prefixes, so I need dinitrogen, 5 oxygens, pentoxide. PCl4, also molecular, so I need phosphorus. Tetra chloride, and AlPO4, that is aluminum phosphate. All right, and you should notice that I did not change the ending to my polyatomic ion to IDE. Polyatomic ions keep their name unless they're part of an acid. Okay, so remember that. All right, moving on. Like I said, I'm going to pick up the pace as we go. So now I have 10 oxide up there at the top. All right, it's an ionic compound. Now the 4 in Roman numerals. Notice I put that there for us. That tells you, right, the charge of the tin in this case. So this is going to be SN4 plus, and oxygen is always O2 minus. So when I combine these, all right, I'm just going to show you how to do it incorrectly real first using the crisscross method. I'm going to get SN2O4. That is incorrect because my ionic compounds always go to the lowest whole number ratio. So a 2 to 4 ratio can be reduced to 1 to 2. All right, so that is incorrect. I'm just going to go with SNO2 in that case. All right, so be careful. There's going to be one like that on the test. 2, right? Be careful. Calcium chloride is an easy one. This is Ca2 plus, Cl minus, CaCl2. Crisscross. Dinitrogen tetrasulfide. So di means 2, tetra means 4, so that's N2S4. Ammonium nitrate. Those are both polyatomic ions. This is NH4 plus, NO3 minus. So that's just NH4, NO3. And notice I do not need parentheses because there's one of each. You only put parentheses around those when you have to add a subscript to it. All right, hydrobromic acid, right? So the hydro prefix tells me it's bromine, not bromate. All right, so it's going to be H plus and Br minus. So that's just HBr. How did I know hydrogen? Because it's an acid. Phosphoric acid, there is no prefix, hydro prefix, which tells me it's not hydrogen and phosphorus, it's hydrogen and phosphate. All right, so it's going to be H plus and PO4, 3 minus. So I need to crisscross my charge here. H3, PO4. All right, and then aluminum hydroxide, Al3 plus hydroxide. Okay, that ends in IDE, so you might be looking on your periodic table for the element called hydroxide something. All right, it's one of those weird polyatomic ions that, even though it ends in IDE, it is a polyatomic ion. It's OH minus. All right. Now, in this case, I'm going to need 3 hydroxides, 1 aluminum, Al. Now, when I have to add a subscript to a polyatomic ion, I need, for instance, OH3. Okay. Now, quick review. Go through, identify molecular and ionic. Okay. Look out for acids. Okay. When hydrogen, okay, is on the left side of your equation, you know it's going to be an acid, and you need to apply an acid rule. All right. You also know it's ionic. Okay. When hydrogen is written on the right side, such as up here, silicon tetrahydride, right? We know it's a covalent compound instead of an ionic compound. All right. That being said, go through that. Right. The only other thing you have to watch out for once you know ionic versus covalent or molecular is the transition metals, right? Because transition metals need a Roman numeral indicating their charge, in which case you either need to infer it here. So in the case of manganese oxide, I know oxygen's a -2. That's why that 2 is there, right? So I then need to infer that manganese must be a +3 to indicate where that 3 came from in that equation. Here, iron 2 oxide, I know iron's a +2 because it's 1 of each, and I know oxygen's a -2, which means iron must be a +2 in that case. Because what has to happen? The 2 things with an ionic compound, they need to come out to neutral. All right? I'm getting a little long-winded. We're going to have a test coming up. So if you're struggling with this still after this video, make sure you come talk to me or talk to somebody who knows how to do this stuff correct every time. All right?